Now, the last presentation is by Valerio Doppio, R&D Manager of ProGold. He got a degree at the Padua University and another degree in journalism at the University of Ferrara. He mainly deals with research and development, and he also carries out quality tests. And the paper is entitled "The Use of ED-XRF Technology to Measure Gold After the Introduction of ISO 23345." And he will talk about the use of this technology in the gold sector. The correct calibration, the selection of parameters, and the understanding of the structure of jewels make it possible to have very accurate results in line with the new standards of ISO 23345 2021. Please, Mr. Doppio.
Buongiorno a tutti.
Good morning and welcome, and thank you for being here. I'd like to start my presentation with a short introduction related to the process of coupling and then the process of XR estimate. Well, you certainly know this fire assay technique, which is recognized at an international level, and it is used for the determination of the fineness of gold. Well, this technique, however, has some limitations because many of the steps are made by hand by operators, and so there is the risk for mistakes. And often there are differences in terms of results depending on the operator which carries out the test. In some big companies, for example, the operators have a specific patent which monitors their work. Now, the X-ray technique has slightly different characteristics. It is not destructive, which is an advantage as compared to fire assay. It does not require chemical reactors or furnaces. It is very fast, and it is practically carried out by the machine, and so the work is not really carried out by human operators. Of course, there are also limits in the use of this technique, and in particular, we will see that calibration of the instrument is extremely important. Well, this technique is based on the excitation of atoms, and so it can be prone to mistakes if the surface and the bulk of the sample are not perfectly homogeneous. And it has only recently been introduced in our sector, so we don't have many data available. Well, we should have a short video about the technique and how it works. I'll try to be very simple. So there is a high-energy source which generates a beam of radiation that is focused on the sample. And within the sample, that causes the emission of electrons from the inner shells. And when the external shells atoms occupy these spaces, these vacancies, irradiation is emitted, which is not generical, but is specific of that electronic transition, so specific of that atom. Now, if we want to measure those outgoing signals, well, we can identify the atoms in the sample and also their relative quantity. And so we have both a qualitative and a quantitative analysis. And so you see the final step in the video. So the technique lends itself to the interpretation of the composition of the sample. Well, what's interesting for us in the jewelry sector is the content of gold, of course. So what has changed recently? Well, recently, the Technical Committee 74 of the International Organization of Standards, that is ISO, has produced a new document, 23345, which is specific for the analysis of the fineness of the jewel by using the XR technique. And our work started off from the publication of this document. So we decided to assess the results achieved during the drawing up of that document. We wanted to see whether we could improve those results and also to see what are the specificities of this type of technique. So we will see now the influence of the collimator. That is the collimator dimension, and whether this is influenced also by the alloy microstructure, because we know that the structure can vary depending on the solidification phases or the contents of some other elements. And then specifically, we will see what is the influence of calibration of matrix elements, and we will make an analysis of the accuracy levels that you achieve in terms of the fineness, and then we will also see the influence of the matrix that is based on the calibration made and the compositions that we try to measure. We will see how the performance changes and whether there are differences. And then we will also see some practical tests in some gold assays provided to us by a partner company, so that we can say that we didn't work only on laboratory samples, but also on real finished products. And we will see whether the results of our study can be applied to actually produced samples. Now, this is the experimental setup that we used for these measurements. Well, we neglected some measurements because they had already been explored in technical terms. So in the literature, you can find papers dating back to 2006 related to the parameters of these tests. So let's start from the first point, which is of interest of us, which is the size of the collimator. I skip a bit of maths. Why is it so important? Why is the dimension so important? Let's make an example. On the left, you see a sample which is analyzed by XR. These are two sections, two examples of the section of material whose signal is involved in the analysis based on X-rays. If we do a fire assay, we will cover the whole sample. Now, if we use the Lambert-Beer equation, what we achieve is this. And if we use a smaller collimator, which is on the left, the fire assay will involve 655 more atoms than the XRF analysis. But if we increase the size of the collimator, this ratio will go down dramatically, down to 59 times. And this suggests that the bigger the collimator and the more the quantity of atoms is similar to the technique used for fire assay. Now, let's have a look at another point, the surface, which also, and the microstructure of the surface, which can have an influence at the time of when we choose the collimator. Here we see three surfaces, small grains, medium grains, large grains. That is a sort of natural grain. This is a collimator. And this is 0.6 millimeters. Well, it's clear that for a small grain, a small collimator will have a certain idea about the grains included in the material. But in a larger surface, we will limit the capacity to detect the number of grains involved in the analysis. In order to check whether this mathematical consideration and also this surface-related consideration are actually affected, we carried out repeated analysis, repeated tests, and these are the results. As you can see, well, the fineness are below, but apart from the fineness, please focus on standard deviations. While in the case of small grains and large grains, the standard measurements were good, both in the case of big collimators and small collimators. In the case of medium grains, standard deviations double as compared to previous case series. Okay. Based on these results, we can conclude that it is better to use the biggest possible collimator, of course, if that is compatible with the sample. And we should pay attention, be particularly careful if our alloy has a large grain or dishomogeneous grains, because this can affect the analysis. Now, let's move to the second element that we have analyzed, that is the effect of calibration. We decided to have three different alloys, 3N yellow gold, 5N red gold alloy, and palladium white gold alloy. And this in order to have a representation both of gold, white, and red gold, and to see how these behaved. And for each of the three alloys, we built a calibration curve using three samples, 75, 76, and 77%, so as to calibrate the surrounding area of these samples. And then we wanted to focus on one specific element, zinc. Why zinc? Because if we look at the absorption spectrum, we see that there is a partial overlapping of zinc with one of the secondary peaks of gold, something that does not happen with other elements such as palladium and copper. So there could be an interference between zinc and gold. And for that reason, we decided to carry out a series of analyses where we checked what happened if we declared to the instrument that zinc was present in the same quantity as it is normally present in these alloys, or if we ignored and did not declare the presence of zinc, thus avoiding that the machine would force the content of zincs. And results can be seen here in this diagram. As you can see, not declaring zinc within calibration apparently improves results. And this is an instrumental limitation of the way in which curves are interconnected, because the machine receives an instruction by the operator to consider the zinc, and so the machine overestimates the presence of zinc. So we explored zinc, but if you use other elements, such as gallium, indium, and all the other elements that you can use in gold alloys, well, you will have to evaluate what is the effect of these secondary elements. Now, let's have a look at the results after making calibration, choosing these parameters on the three alloys that I mentioned earlier. Gold alloy, where we wanted to see whether there was a difference between the fine grain microstructure and the large grain microstructure. And these are the results that we achieved, and that are summarized in these two slides. And then we also did fire assay. So you see that there are slight differences in terms of fineness, both with fire assay and with X-rays, which are probably due to the fact that in order to obtain large grains structure, we used a different production method. But if we compare the results between the X-ray analysis and the fire assay in fine grain and large grain alone, well, we see that mistakes are not so different, and they are lower than half mm. Only in the case of large grain, medium grains, the number increases slightly due to surface dishomogeneity. And we will see that this is not present in other colors. Now, if we look at the same set of analyses for red gold, these are the results. A compatibility of the results between fire assay and X-rays, and some comparable mistakes, and in both cases below half mm. Again, we see the values, and after making our tests again, this is what we achieve. So, correspondence between X-ray analysis and fire assay within the limits of measurement errors. And please consider that the fire race regulation establishes that when you do repeated tests, values are acceptable if the difference is within half mm. So we're very close to the results that have already been achieved. So we could also think that the results in this case are even better. And the limit of fire assay for palladium is that palladium doesn't dissolve so easily, and so you have to take that into consideration. Here you see a diagram of what I just said, and you see that apart from the first case of yellow gold, there is always a good correspondence between the fineness achieved with the fire assay and with X-ray. So the performance of this technique for the alloys considered and for these measurements is very good. Now, let's have a look at other parameters. What happens, for example, if instead of using a calibrated method for a specific composition, I want to measure the fineness of gold of another alloy? I'll make an example. And we crossed some data. We took the red gold and we used the same method that we had used for the yellow gold, and that in order to measure the importance and the influence of matrix. And we see it here. Basically, there is a wide error if we use the white gold method with red and yellow gold alloys, and vice versa, because there is an element which is completely different, and which is palladium, which causes variations in terms of results. And there are also variations between gold, yellow gold and red gold, which have the same composition. So basically, we shouldn't use methods for different colors, but if we concentrate on just one color, so let's take our red alloy, and instead of analyzing it with its specific method, we can use methods for other red gold alloys with a higher copper percentage. And this is the result that we achieve. Above, you see the original measure, the calibrated method. It's in the red circle. And below, you see the results achieved by other methods. You see that in the case of alternative methods, where we have a composition which is pretty similar, and with a large quantity of copper, we have good results, although they are not perfectly in line with the results achieved with the specific test. While as we go towards pink or yellow gold, we will find those big differences that we had found in the previous test. So what can we deduce? That for small deviations from the real value, we have results which are in line with the previous ones, while as compositions differ, our results will worsen gradually. We still have to establish whether there is a lower limit which requires a more systematic test. That is, what can be the difference between the compositions used, and that in order not to excessively affect the results. Now, this is the last part of our research work, and it is a case study on two different samples. We chose two lines of products. It's important because these two products are produced with completely different techniques. One is produced by mechanical working and the other by investment casting. So this is the experimental setup that we used in the light of all the results obtained previously. You will note the dimension of the collimator, which is 0.6 millimeters. It is the biggest collimators that we could use on these specific objects. Now, let's start from this ring. With the addition of the results obtained previously, while in orange you see the results of the fire assay on the various types of the ring, and in blue you see the results of the X-ray technique. And this is investment casting produced. And we see that in almost all cases there is a compatibility between the results obtained with the two techniques, with the exception of 3 cases where there is a difference between the two fineness, although it does not go beyond 1.2. Well, this is an investment casting product which, in case of colding, etc., actually has some lack of homogeneity, and so it can be affected by the fact that XRF is a surface technique. Now, if we look at another type of product, this is what we achieve. That is perfect compatibility between the two results. So, in conclusion, what is the result of our work? Well, calibration methods are fundamental in order to guarantee the accuracy of the measurement by means of X-ray. And as you could see in the previous slide, it is indispensable that the method used for the analysis has been calibrated based on an alloy which is as close as possible to the object that we want to test, because if the deviations are very small, well, they can have an impact on the fineness, on the evaluation of the object. We've seen that zinc can have an impact on the performance of the measurement, and so we need to consider the effects of these elements on the performance of the instrument. And then we have seen that we have to use the biggest possible collimator in order to maximize the statistics about the atoms measured, and then we have to look at the homogeneity of the microstructure. And then we have seen that the X-ray analysis can, in some alloys and under some conditions, can be comparable in terms of performance with the fire assay. Well, this doesn't mean that we ask you to move from fire assay to X-rays, because both these techniques have their weak points and their strong points. But the X-ray technique makes very fast analysis and does not destroy the samples. Well, it could be a good basis for a wider exploration of the pieces of production without focusing on the model sample and enabling us to test all the objects of production, and then to make a fire assay only for those elements where we think that there are some criticalities. Clearly, in the next few years, we will have to further investigate the performance and the possibilities of these instruments which are spreading, and more performing models and more accurate models are being produced, and the ISO regulation is pretty young, so to say. There is the possibility of improving it so that we can use this technique widely within the sector. With that, I conclude, and I thank you for your attention.